All right, ladies and gentlemen, I want to take this opportunity to welcome all of you to the Valley of the Shadows of Advanced Quantitative Research. It's a pleasure to have you. The last time we looked at correlation, we ended with correlation with p-values. Correlation with p-values. We're looking at the data set known as the Burkutu ventures. That data set was made up of two things. We had the Burkutu coded, and we also had the Burkutu for R. Okay? And we used that data to do all of the things. Today, we want to begin by the real use of econometrics, starting with simple regression. But before we start with simple regression, let me just tell you a little bit about econometrics. Please pay attention, because if normally you don't pay attention from the onset, you get confused at the later set, at the outset. Econometrics come from two words: economics and metrics. Okay. Normally, the metrics here looks more at mathematics and statistics. So econometrics is a combination of economics principles, economic theory, and statistical and mathematical knowledge. And it involves several sampling of data. It involves econometric models. It involves estimations and inferences. We have already looked at inferences in statistics by looking at hypothesis testing. Okay. And now we want to do bigger things with that. There are three types of econometrics: cross-sectional, time series, panel data. Now, cross-sectional means that you have one point at a time that you want to consider the observation. So let's say that you want to consider all the countries in Africa, their GDP. And you want to see the impact of consumption, investment, government spending, and net export. You want to see individual impact of these on GDP, but you collected the sample in 1 year. That is cross-sectional. That is cross-sectional. Time series is when you take a particular variable and you look at how the variable is looking like over a long time period. So if you take inflation, you are not checking inflation against African countries, no. You have taken the inflation for one country and you have looked at the inflationary trend over time from 1950 to date. That is time series. It's normally used in stock market analysis. Panel data econometrics uses longitudinal data or panel series. In other words, you get the observations not only across individuals, but also across time. So looking at the example, you have the GDP, the inflation, the exchange rate, the interest rate of not one African country, but several countries and over several time periods. That is panel. It's a master of all data types. But what we want to look at now is a cross-sectional. Because once you understand the cross-sectional, you should be able to understand the rest. Cross-sectional is a foundation. Please get this. Econometrics is not for economics. Not anymore, after all. It is not for mathematics, not even mathematics, it's not for statistics. Now, econometrics is being used in public administration. Econometrics is being used in health services management. Econometrics is being used in marketing, information systems, political science, environmental analysis, energy economics, accounting, psychology, sociology, Even classics, medicine, econometrics is happening there. So if econometrics is being used there, how much more in finance, operations, accounting, economics, statistics? So that is why you want to appreciate it. It's used a lot in political science. It's used a lot in public administration. In fact, some of the papers I'll give you, you will realize that econometrics is necessary for that. I hope you understand at this stage. If you don't understand, quickly let me know before we proceed. We are going to pick regression, which starts with econometrics, because we've already looked at correlation. Now, remember the correlation you did. It deals with association. But regression deals with causality. The last time we were able to go through a lot of differences between correlation and causality. The fact that certain things are correlated does not mean that they are, they have causal effect. We looked at multiple examples. We debated it. So what is regression? Regression uses statistical measures to analyze, infer, predict a dependent variable. And then how that dependent variable is related, the nexus. The nexus here means linkage. So you want to examine the linkage or the nexus between a dependent variable and multiple independent variables. These multiple independent variables are also called predictors, regressors, predictors, regressors, or explanatory variables. Please take note. The dependent variable is also called response variable. The dependent variable is also called outcome variable or explained variable. When the dependent variable is 1 and the independent variable is 1, what kind of regression is that? You can tell us. When the dependent variable is 1, Emmanuel.
Prof, I believe it's a simple regression.
It is a simple regression. Now, when the dependent variable is 1, but the independent variables are more than 1, what kind of regression is that? Noah.
Multiple regression.
Good. When the dependent variable is 1, but some of the independent variables are categorical, others are numerical, what kind of regression is that? I hope I haven't tricked you. When the dependent variable is 1, okay, the independent variables, some of them are categorical, some of them are numerical. What kind of regression are we talking about here, Francis?
Well, I think we are looking at dummy variable regression in this case.
It is a dummy variable regression. Guys, open your eyes. When the dependent variable are more than 1, and the independent variables are also more than 1, being categorical or numerical, what kind of regression is that? Oh, this is deep. Let me see whether we have the smartest person around. So the dependent variable is no longer 1. It could be 2 or even more. And the independent variable are still categorical and numerical. What kind of regression is that? That got you. Let's see. Kingsley.
No, logistics regression.
Logistic regression is just one of them. But there's a body of name for them. Francis.
I think we are looking at multivariate regression.
Multivariate regression is the same as multiple regression. but you are close there. It's known as limited dependent variable regression. Limited dependent variable regression. Okay, because the focus is on the dependent variable. Now, multivariate, you are looking at structural equations modeling. Okay, multivariate, multiple dependent variables, multiple independent variables, you're looking at structural equations modeling. So get your hold on this, and most of you will use this thing. Okay? You will not use the simple one we're about to do. But of course, in order to appreciate everything, you need to know the simple one first. So let's begin. So here you have on your screen simple regression, multiple regression, and then you have one of the limited dependent variable regression, which is known as logistic. Guys, apart from logistic, do you know any other limited dependent variable regression? Who does? Apart from logistic, Kinsley.
Probabilistic.
Probabilistic, good. Okay, and please, those who don't know, write them down. You see them somewhere, write them down. What else, Francis?
We have sensor regression, which would be truncated or Tobit regression.
Good, write it
Tobit
down.
or Probit.
Write it down, write it down. You see, the thing is that if you don't write it down, you will see later on that is what we mentioned some time ago. Write it down. Write it down. Don't say that I'll never use this thing. Write it down. You're a scholar. At this stage, you are becoming a doctor. So it's important that you put everything down and research later. Don't say that my job, my mother, my father. Okay. So you have Tobit, you have Probit, you have censored, okay, like truncated regression. Okay. You have fractional systems regression. Okay. All of those logic, all of them, you have these things as part of them. And you got to know the nitty-gritties of all of them. It's very important. Let's take practical things. Application. What is the essence of doing causality? Well, one of the areas is that you can apply it to future sales of a product. Based on the past buying behavior, you can predict how much will be sold next time. Regression can help you. Regression can help you to know the economic growth of a country next time. You can predict. You can predict the number of runs or goals a player will score in the coming matches based on previous performance of that player. You can do that. You can predict how many goals Ronaldo or Messi or Haaland is going to score. You can predict that using prediction and regression analysis. You can predict how much to pay to a new employee based on the years of experience of that employee. You can use regression for that. You don't need to worry yourself. How much houses to sell in the coming month and at what price? You can use regression to predict that, to forecast that. You can use it to forecast petroleum prices. You can use it to know the price of a particular stock for tomorrow, how long a person will stay in a hospital. You can use prediction to do all of this, and these are practical. You see, the uncertainty in the world can be predicted. You can know with certainty the uncertain factor by knowing and understanding and applying regression. So the main goal of a regression is to establish causality. That's number one. And then to predict. Now, you establish causality means you want to know the causal link and how much is the link. And then you want to also use that to predict for the next, what you don't know. So first, you want to know what should be known. After knowing what should be known, you can now predict what is unknown. That's regression for you. That's regression for you. Now, you can apply regression to spending. You can look at the link between spending and revenue. You can look at the association between a person's education and income. You can know the impact of hours of study on the grade of a student. You can use regression to do that. In the medical field, you can use it to understand the connection between drug dosage and the blood pressure of a patient. In medical field, okay? Okay, you can use it to look at the effect of rainfall and fertilizers on crop yield. You can use regression for that. And these are all PhD-able topics I'm giving you, by the way. Okay, you can look at the effect of a parent's education and the residents on the kids' education. You can do that using regression. Okay. So there are so many things that you can do with regression. Now let's come to the nitty-gritties. I'll spend some time here because what you see here is very deep, very deep. So pay attention. A regression is a model. What is a model? A model is a representation of reality. You know, when you take a picture, you take your phone and then you decide to take a picture. And then you take the picture and then you look at the picture. What is that thing on the camera now, on the phone? That thing you are taking, what is it? What is it? What is that?
So I would say it's a model of your real life.
Exactly.
Or one picture.
Exactly. It is a model of your real life. It is a model of your reality. That model, it can help you to do other things. You can use that picture to do other things. A regression model tells you the relationship between certain things and certain things. So let's look at the first relationship. The first one you have here is the dependent variable, and it's always on the left-hand side. Take note. We have called it Y, but you can call it any other name. So if it is sales, then this one becomes sales. The dependent variable is a variable that depends on the independent variable, X. Remember, in this case, it's a simple regression because the independent variable X is only 1, and the dependent variable is only 1, Y. What is the connection here? This is what a connection is saying. The connection is saying one directional only connection. So the independent variable is supposed to be influencing the dependent variable, not the other way around. Well, at least that's assumption. Assumption is that the independent variable is influencing the dependent variable. Now, but the question is that by how much is it influencing the dependent variable? The coefficient, also called the parameter, okay, or the betas, the beta parameters, will tell you by how much the independent variable or the regressor, by how much this regressor affects this regressand. How much the regressor affects the regressand. That by how much is the value of the beta. In this case, beta 1. So betas, which are attached to the independent variables, are telling you by how much that particular independent variable is affecting the dependent variable. It is telling you the marginal effect of each independent variable on the dependent variable. There is one particular beta that is not having any independent variable with it, beta naught. And it is said to be the slope of the regression in this case. It is said to be the slope. Now, what is the use? What is the mean? What is the economic use of this? Well, the answer is that it has no economic usefulness or economic interpretation. It is for cosmetic purposes, but it has one particular use. And keep that in mind, prediction. Prediction. So if you want to ever do prediction, that beta naught will help you to be able to do the prediction. Because if none of these variables are there, the beta naught indicates that something is there, which has some relation with the Y. And that leaves us with the most important thing in a regression. The last one, and the most important, the error term. I want you to know the other names of the error term. There are about 7 different names of the error term. Who can give me one? apart from the error term? What is another name for the error term? Let's be quick with this. We have a lot to do. What is another name of the error term? Yeah, go ahead.
So the residual.
The residual is another name. What else? Residual is here. What else do we have? Derek.
It can be noise.
Random noise.
Noise.
What else? Francis.
Also, we have the idiosyncratic error.
The idiosyncratic error. Look, if you don't know, write them down. Noah.
Prof, disturbance term.
Disturbance time. Very good. What else?
The stochastic error.
Stochastic noise. Good. What else?
Unexplained variance.
Unexplained variance. Good. What else? How is it? Systematic error. Okay. All right. So you finally have the unobserved heterogeneity. The unobserved heterogeneity. Guys, what is the use of this error? Well, first of all, you just said that there's a relationship between this independent variable, also called explanatory variable, and the explained variable. You said that. But there are other factors. There are other factors beside this X here that can affect the Y, but have not been captured. And these factors are captured by the error term. The goal of a regression is to model so that the error becomes zero. And this is said to be the expected value of the error term is supposed to be zero. The essence of the regression is to estimate the model. And so here you can see that we are talking about estimated regression model. Once you estimate the regression model by using a principle called fitted line or OLS, we shall come to that, you will now be able to get a new regression, no longer a model, but an equation. And this is the equation. In this equation, you will notice that the Y is capped because we now know the actual relationship. And you can also see that the betas are capped because we know the actual value. So as an example, you can see here that we have an actual value after going through some rigorous procedure. We have been able to obtain the actual value of the beta naught and the actual value of the beta 1. Once you have this, it is known as the estimated regression equation. It's no longer known as the specified regression model. And at that stage, you will notice that the error term is zero. The error term is gone. So when you have estimated the model, the goal is that you expect the error to be zero. Good. Now let's get a little bit deeper into this point that we've indicated. How is the estimation done? Remember, it is a process of minimizing the error that will eventually lead to the beta parameters that you wanted. And these beta parameters are now no longer beta parameters, but they become coefficients. Coefficients in the sense that they are now values, numerical values, and not Greek letters anymore. But the approaches, okay, the approach is to convert the estimator to an estimate. The estimator is when it is unknown. The estimate is when it is known. Please note that sometimes I'll be using epsilon, the Greek letter epsilon, to refer to the error. Sometimes I'll be using U to refer to the error. Okay, don't worry about that. To get the estimator, also called beta parameter, you will use one of the approaches called OLS, ordinary least squares. by Adrien Marie in 1805. There's other approaches like maximum likelihood estimation by Fisher, generalized least square estimation by Atkin, feasible GLS, that is feasible generalized least square, and then the weighted least square. All of these are possible ways of coming. But we just got to focus on the OLS for now. In higher levels of study, we'll look at all of this. What is the OLS, the ordinary least square? What is that? Well, it's an approach of estimating the beta parameters. How is it done? Well, in order to appreciate how it is done, let me just give you a simple scenario, very simple. If you take a small sample data, okay, a very small sample, and then in that sample, you can have the price of a house. So let's say house price, okay, and then this house price, and then you have the size of the house in square meters, okay, the size of the house. So let's say that when the size of the house is, say, 300 square meters, the price is, say, $40,000. When this one, the size goes up to 500 meters, this one goes to, say, $48,000. When it is 200 meters, okay, this one goes to, say, $38,000, and then on and on and on. What you do normally is that you can scatter plot this data, 40 against 300, this one against that, this one against that, this one against that. And when you do that, you will have a scatter plot of information like this. So this is one scatter plot, another scatter plot, another scatter plot, another scatter plot. At that time, there was no line. And you now know a particular house size. Let's say you know that a particular house size now is 1,000 square meters. Knowing that we know that this one is 1,000, we can help you to predict the price of that house because the regression line will be able to do that. Now, how does the regression line come in? Whilst you have this, you see that there's a distance between each plot and then the line. Now, you later learn, how did you even get a line in the first place? There's a distance between each plot and the line. This distance is known as the error. The error here is the distance between the actual value and then the expected value. So the value that should have been this very one is here. That is expected value. So it's like we create an expected value for each of the actual values. And that expected value forms a straight line for each one. And we look at the distance, how far you are from the expected, between your actual and the expected value. And that is known as the error. So that error is it. And you can see that when you are above the line, your error is positive. When you are below the line, your error is negative. Our goal is to minimize your error so much that you don't have any error. That means you are now on the line. It means that your actual is now equal to your expected. So that means that we have squeezed and minimized the error to that point. That is the essence of regression here. And so that your actual value becomes equal to your expected or predicted value. This is a graphical demonstration of how the regression is going to do that. How does it really do that, honestly? Well, regression will do that by OLS, creating the least square line. So it will create the least square line. It creates that line by minimizing the error. But you see, some of the errors are positive, some of them are negative. So minimizing it is not good. So in order to clear the negativity, you square each of the errors. So if the top one is +2, but the down one is -3, okay, you want to sum them. You want to sum them, but you can't sum them. So you need to square them to clear the negativity before you sum them. So once you square each of them, the negatives vanish. Now you can square. Once you square them, you can now sum the error squared. And once you sum the error squared, then before you minimize, because remember, they're all on the same line, before you minimize the entire line. So we are going to use some beautiful mathematics to find the beta parameters. Please pay attention because this might be a little bit abstract at this stage. So we're going to minimize the residual, the error, but we are minimizing the sum of the squares. So first you must have an error. Sometimes you call it ESS. So you must have an error. Okay. You must now square the error and then take the sum of the error. This is what we are minimizing. So we are minimizing the error sum of squares. The error sum of squares. I wrote ERR, is supposed to be ESS. All right. We are doing that because this is the gap between the actual values and the predicted values, the actual values and the fitted values, the actual values and the expected values. Okay. And that is what we are minimizing. Keep that in mind. How is the minimization done? But remember, anytime you hear the word minimization, then the whole idea of differentiation and integration come into the picture. So first, let's get the error. The first thing is that you have your regression model, the basic regression model here. Look at it carefully. Oops. And this is a basic regression model. Let me just go back here. Now, normally when you have it boom like that, it can be confusing, but don't worry. Okay, this is a basic regression model. We have explained this already. Now, this error, if I take all of these to the left-hand side, you have y minus that. But this very one is the predicted. The beta naught plus the beta 1x alone is a predicted. So the error is the actual here minus the fitted or the predicted. Now, you can see that I've now replaced this predicted by that into the formula. And now what you got to do is to square each of them. So when I had this, I decided to square the whole of this. And that's what I've done here. Because remember, we said we should square them and then take the sum. And then I took the sum using the summation symbol. So now we have the sum of the squared error here. Now, what are we looking for? We are looking for the beta naught, and we are also looking for the beta 1. Now, if you look at it carefully, some of them are squares. So anytime you have something, for example, in the good old days, if you have y equals to 2 plus 4x squared, if you find dy dx, okay, using the basic partial differentiation, you are going to multiply the 2 by the 4, giving you 8. Then you write the x, you subtract 1 from the 2, and that gives you 1, which is still x here. So this gives you the answer of x. And then you set this x is equal to 0. And then you can find x from the story. Do you remember that? Do you guys remember those good old days? Okay.
Yeah, Doc, we are struggling, but it should work.
All right, let's move on. Okay. Now, what you now do is the same thing here. Okay. The same thing, nothing changes here. All you're going to do is going to take this thing, you're going to differentiate the whole of this thing with respect to beta naught. Beta naught. Okay. So anywhere there is no beta naught, you ignore it. If you differentiate this thing with respect to beta naught, well, remember the summation is multiplying beta naught. But then all of them are squares. So technically, beta naught is to the power 2. Okay. So that 2, you bring it to the summation symbol. Beta naught has a negative sign in front of it. Okay. So you have that negative 2 with a summation symbol, and everything is as it is here. Okay. It has only helped you to clear the square. you will now divide both sides by -2. On the left side, -2 here, which means that the right side is still going to be 0. The -2 is going to cancel. And you are left with the whole of this one without the square. So the summation will now multiply the y, the summation will now multiply the beta, the summation will now multiply the beta naught, the summation will now multiply the beta 1. And that's the next step we are going to do. We'll do the same thing with the beta 1. Remember, I'm doing it with the beta naught. I'll do the same thing with the beta 1. Okay, so now let's continue with the beta naught. So this is what I just did. You multiply each one by that, you divide both sides by the 0, by the -2, okay, and they are all gone. So if you look at here, if I divide both sides by -2, or even if you take the -2 here, look at it. If you apply the -2 to all of them, if you apply the -2, you're going to have -2 summation y plus 2 beta, sorry, plus 2 summation beta, then plus 2 beta 1 summation beta 1x, or beta 1 summation x. You're going to have this. But just note that the first one alone will be minus, the ones in the bracket to be plus plus. That's all you have there. The first one here is minus, then the ones in the bracket will be plus plus. So you have this one to be plus here, you have this one to be plus here. The 2 is gone. The 2 is gone. Now, at this stage, I can move this one to this right-hand side without touching these 2. And when you do that, you will have summation y. Nothing has changed. But look at this. This is a summation. Summation of what? Summation of ones. And these ones are the number of observations. And so the summation of the number of observations is equal to the sample size. So this becomes n. And then you bring your beta 1 out, then you have summation x. Now, but what is that summation x? Watch it very carefully. At this stage, I can divide both sides by n. Let me just show you. Okay. If I come here, I can divide both sides. So the left-hand side, I can have summation y, okay, equal to summation beta naught, I'm picking it from here, okay, plus beta 1 summation x. That's it. And then here, divide both sides by n. Okay. No, you don't divide both sides. You divide both sides by n because this one has got n. Okay. What you have here, when you sum all of them, you get n. So if you divide all of these by n, it cancels this because remember this one is an n by 1 matrix. So it becomes n. Then you divide this one by n, you divide this one by n. So this one steps out. So you now have beta naught because that one is gone by itself. And then you have beta 1 sigma x over n. And sigma x over n is actually x bar, is a mean. Okay. And sigma y over n on the left-hand side is also y bar, which is a mean. Okay, and remember this one is minus anyway. Don't forget. Is it minus? No, it's not minus. We've already killed the minus. Okay. Now, at this stage, if you want m beta naught to be out, if you want this beta naught to be out, all you got to do is to move this one to the left-hand side here. So beta naught becomes equal to the y bar minus, because when it comes here, it becomes minus beta 1 x bar. And so we have been able to find the value of beta naught. At this stage, because we found it, we can say that it is now capped. Okay, the beta naught is now capped in this context. Of course, by then, you would have also found the beta 1, and so that would also be capped. So all you got to do is, if you want beta naught, you have to find beta 1. Take the mean of the x, take the mean of the y, and that will give you finally the beta naught. But how do you find a beta 1 in the first place? Let's do that one. Okay. The same principle. You go here, you differentiate this time, not with respect to beta naught, but respect to beta 1. That's it. So watch it. Watch it. And again, if you are stuck, let me know. Okay. It looks manya here. I didn't want to show it manya. But don't worry. Don't worry. I'll go through steps. I mean, normally, I did my thing to be pausing so that you see it step by step. But all the same, let's do it. In fact, I've gone too many steps so that you get it when you sit down. So watch it. I'm differentiating everything with respect to beta 1 now. When you go to the equation itself, remember it was squared. So when you differentiate everything with respect to beta 1, that comes here, it becomes minus 2. Now, why is it minus 2? Okay. And watch here. Let's go here. You are differentiating the thing with respect to beta. Where is that? You are differentiating the thing with respect to beta 1, and there's minus in front of beta 1. Okay. Remember, there's minus 1. So you take the 2 multiplying the negative 1, okay, which becomes negative 2. Before you write all of these together and then subtract minus 1 from the exponent. So that's basically what I'm doing there. So that is how come you got the minus 2. And then everything is inside a bracket. But remember that in partial differentiation, there was x attached to the beta 1. And because there was x attached to the beta 1, that x must also be part of this. It's everything that is attached to beta 1. In the beta naught, there was nothing, so we left it. But this one, there was x. So you have to bring the minus 2 together with the x. Just as if it was y squared, y equals to 10 plus 4x squared. You multiply the square by 4 before you now do the subtraction from the exponent. All right. So that's what you're doing here. So you take this one, minus 2 sigma x. The sigma is already there. And now you set it to 0. Anytime you differentiate, you set it to 0. Now forget about this left side here. Okay. Forget about this whole thing now, and then let's focus on only this one here. Now you're going to expand because the thing has been factorized, as you can see. So you're going to take the minus 2 sigma, and then the x, you're going to multiply it by the y. So that gives you minus 2 sigma xy, or yx. It's all good. But that is going to be minus because there is plus in front of the y. But when you multiply this one by this, it's going to be plus. So you see that it's going to be plus 2, and it has sigma x before the beta. It's as it is. It's cool here. When you multiply this by the next one, it's going to be plus. So it's going to be plus 2 again, then the beta x. But remember, there is x here, so you have another x multiplying x, so then you have x squared. Cool. Now you are looking for what? Beta 1. You're looking for beta 1. Now, the one way you can do for beta 1 is move everything here to the right-hand side. Move everything here to the right-hand side. And beta 1 will stand. But they all have 2. 2. So why don't you kill the 2, first of all? Okay, I kill all the 2. The 2 is gone. Okay, good. Now, you are left with beta, sigma beta 1x2, which is what you have here. I've deliberately decided to bring the beta cap, the cap on it, because we are going to find it anyway. So this one is going to be equal to, remember, when you move these ones here, the minus here becomes plus. Yes, Noah?
Yes, Prof, if you are killing the 2, won't you divide the right-hand side by 2?
Yeah, but when you divide the right-hand side by that, it will still get 0. 0 divided by 2 is 0, isn't it?
Yeah.
No, you get it.
All right, okay, cool.
So 2 people are going to share 0 thing. Each one will get what?
Understood, Prof.
All right. So that one is gone. And so you are left with beta naught, beta 1 cap, sigma x, which is here. But because you move this one to the right-hand side, it becomes plus here. Remember, it becomes plus. And this one, this second one, sigma x beta naught, it was plus here. So when you move it to the right-hand side, it becomes a minus. Okay? And I deliberately set it to equal to 0 again. It doesn't spoil anything. Everything was equal to 0, still equal to 0, nothing. Now, at this stage, you're looking for beta 1. What do you think you got to do? Well, one thing you can do here is look at these two here. Okay. If you check carefully, this beta naught here, if you check carefully, that was the value we had already gotten. This value, we got it from the previous one. That beta naught cap was y bar minus beta 1 cap x bar, if you can remember previously. So I'm just coming to substitute it because I already have it. I substitute it here. Oh, now it gets beautiful, I'm telling you. Because now that I've substituted it here, I can now expand here. So I can multiply this sigma s by the y bar, okay? And y bar as it stands itself is sigma y over n. So when I take this one to multiply this, it's like I now have sigma y over n here, which is what I'm having here. And then I'll attach my sigma x. Okay, good. What about this one? This one, remember there's minus here. Okay, so that's why this one is minus, but this minus will make this one plus. Okay? So it becomes minus minus, making plus beta 1, which is what you have here. Plus beta, and then it's multiplying this sigma x outside, but then inside it is sigma x over n. So now the sigma x at the top will become 2, because this very one is sigma x, but it is over n. But this one is sigma x, so you now have sigma x squared over n. And I know you get it. Okay, so this part is broken down at this stage. Cool, we set it equal to 0. Forget about these ones. These ones are all cool. Nothing has changed there. It's just from here that we change. Now at this stage, there's something beautiful there. Watch it. You can see that we have beta 1 here, and we also have beta 1 here. So they are like terms. You got to group like terms. So I move this one, beta 1, all the way here. It becomes minus. Don't forget. Once it becomes minus, it carries its sigma x squared over n. So I bring it here, but it becomes minus, which is what I have here. And now I can factorize out the beta 1 cap, which is what I did here. These other ones are left as they are on the right-hand side. They haven't changed. So I leave them as they are. They haven't changed at all. So at this stage, these right-hand side haven't changed. What I have is this one. All I want is beta 1. And if I want beta 1, I divide both sides by this value. I'm going to divide all sides by this value. So that when I divide all sides by this value, it will cancel this, leaving what? Beta 1. Then the right-hand side here will be divided by that. Now watch how you manipulate it to the end. You know when you are dividing something by something like this, and they are all having fractions, as you can see here. Okay. When you divide, it is like what you see here is the whole of the right-hand side divided by this one. And this one here, watch it, this one here doesn't change, but this one divided by n, this one here is divided by n, but this sigma y is also divided by n. Okay, so that is cool. They are all divided by n, so that is cool. So I can make each one of them x bar, which is what you have here. But where is this n coming from? Okay, now watch this. You have this sigma square, okay, minus sigma x square. Okay. This sigma x square, if you look at it, this sigma x square is sigma x over n, or better still, sigma x all over n. And sigma x all over n is x bar square. Now, ideally, you might say that the x bar square is sigma x over n times sigma x over n. Okay, ID. That is what it is. But then the N is already there because of the divisional symbol that you already have there. And therefore, this one becomes, the final of this becomes that. And guys, you can have this because you have data for X, you have data for Y. So once you have data for X, data for Y, you come and substitute it. The N is a sample size. Come and substitute everything, and you can have the value of this. Now, when you put in this and get this value, you can now go and find your beta naught because you already have the value for that as well. This is how you estimate the beta parameter. This is your first great exercise at advanced level of how to find the beta parameter. So this is an econometric or a very great way of finding the beta parameter. What is our goal in regression? What is our goal? Remember, our goal of the regression is to find the betas. That's it. Each beta, we need to find it. Whether it's beta naught, beta 1, beta 2, beta 3, beta 4, we got to find it. We got to find it. We got to find it. And this OLS, ordinary least squares, approach helps you to find the betas. But OLS has got some couple of issues. In machine learning, in artificial intelligence, machine learning, deep learning, robotic engineering, you will notice that sometimes it has some couple of issues. So there's another way that you can estimate the model, not only using OLS, but using other approaches, especially when there are problems in your data. And we'll look at some of these problems, not today. For example, when you have problems like multicollinearity and other things, you can use another approach, which is known as ridge regression or lasso regression. Please remember that you should learn this thing on your own. Okay? But the thing about ridge regression and lasso regression is that they are also minimizing. Don't forget, they are still minimizing. Ridge regression is minimizing. Lasso regression is also minimizing the error something. Okay? And it's the same as the one we did. If you look at what is inside, it also squared it, but it has only added something to it. That's all. It's only added lambda to the whole picture. That's ridge regression. And lasso regression has not added lambda, but then added lambda with absolute value of beta, sum of absolute value of beta to the way. And this method is referred to as the least absolute shrinkage and selection operator. This is another approach. I'm not going to go into the nitty-gritties of how to find it. You might never use it unless you are in a very quantitative area where you have to handle some multicollinearity, heteroscedasticity, autocorrelation issues. That's when you might need it. Then finally, there's another regularization approach, which is known as elastic net. Elastic net. It's just like the previous ones. That one too, in addition to the OLS one, it has also added something. That's all. Okay. So you can see that the first term has added this. That is the ridge regression. The lasso regression has added that. And then the elastic net approach has also added this one. All of these, you can put them in the software and you get the answer straight on. Okay. All of these are penalty terms. Penalty terms. And then the lambdas you see are tuning parameters, which would decide the importance of the penalty that you are giving to it. So all of these are extensions of the OLS with the extra penalty on the coefficient or the weight. And the goal of this is to maximize the generalization by minimizing the errors. That's all. Cool. Now, another approach, and again, I'm just giving you an approach. You're not supposed to use them all the time. Another approach is using the support vector regression. Again, when you look at it, this one uses a proper minimization approach. You're minimizing the sum of the beta squares is subject to the errors. Okay? Subject to the errors. Now, if you look at this and you compare that with the OLS that we did, the OLS was this. This is the OLS that we did. But this one is using a proper minimization approach on the beta parameter, not the entire errors. But then this support vector actually uses the errors as the absolute value of the error as the constraint in the minimization process. Okay, so all of these are ways you can look at the regression. Now, the most important one for today. Before you can undertake a regression, you must assume certain things are there. What is an assumption? An assumption is certain things that are supposed to be there before certain things can work. For example, when I tell you that the university has reopened and lectures have started, just by making that statement, you already know that what has happened. Who can tell me? Just by making that statement, you already know that what has happened. Who can tell us? Lectures have started. By making that statement, you already know that what has happened. Yeah, who can tell me? What has happened? Kingsley, are you here? Kingsley.
Hello, Doc. I'm here.
Can you guys really hear me? Are you with me? Or I should keep going?
Yes, I am with you.
I should keep going as if you're not
Doc,
here. Please, when I call you,
I'm
respond.
here.
Don't wait for anybody to respond. Okay? When I call you, respond. Don't wait for anybody to respond before you respond. It's very important. Yeah. You see, once some of you normally see mathematics like this, you get completely broken. Some of you even leave the group, which is not good. The essence of life is to face death. I want to repeat that. The essence of life is to face death. You don't run away. When your house is leaking and you are sleeping and you realize all of a sudden the house is leaking, water is coming, it's raining. You don't just leave the house because it's raining everywhere. What do? You face it. You seal the leak. You seal it. When things are hard, you don't go for holidays. You don't run away. You don't close your mind. You don't shut down your molecular powers. You face it. You fight it. You go through your Red Sea before you can get to your Canaan. Because the destination matters. But you got to go through the process before the destination will matter. Okay? So sometimes people join the calls, and then when they are learning and the thing is a little bit not clear, they switch off. Don't switch off. Don't switch off. Okay. Before you can undertake a regression, you got to assume certain things are there. And one of the things that people sometimes do is, oh, don't worry, I'll watch the recording and I'll get it. You won't get it. You won't get it. It's when you will normally watch it live that you can ask questions and get it. Okay. So before you can undertake regression effectively, you got to assume certain things are there. If those things are not there, the regression is not great. So these are the properties of the OLS estimators. These are the assumptions of regression. They are sometimes called the Gauss-Markov assumption. Sometimes they are called a classical linear regression assumption, the Gaussian regression assumption. The first one. And you want to learn this because it cuts across everything we shall ever do ever again. Zero mean assumption. This assumption says that the error term, you expect it to be zero. We expect the error term to be zero. By the way, that word expectation of something in finance, it will tell you that it is the mean. The expected value of something is the mean of that something. And so the expected value of the error, given any of the independent variables, is supposed to be 0. The mean of the error is supposed to be 0. You see, that is why you remember that each of the observations has got an error. Some are positive, some are negative. And then we try to square them to remove the positive or negativity. And then we minimize the error to a value of what? What is the lowest value? 0. So we minimize the error to 0. So what are we trying to say? That we are trying to say that the relationship between sales price and the size of the house, that relationship should be strong. But for it to be strong, there must be no error influencing, disturbing that relationship. That is why the error is sometimes called disturbance term. It's disturbance term because it can disturb the relationship you originally have modeled. And so one of the assumptions of regression is that ensure that the expected, ensure, will ensure, so ensure. Ensure that the expected value of the error term is 0. Number 2. So this is sometimes called weak exogeneity. Okay. In panel data, this one is all cross-sectional data. In panel data, it will lead to something known as strict exogeneity. Don't worry about that. The key point is that weak exogeneity here is the same as 0 mean assumption of the error. 0 mean error, 0 mean error, 0 mean error. Keep that in mind. The expected value of the error should be 0. The mean of the error should be 0. In other words, there must be no errors. There must be no mistake in the estimated equation. That is assumption 1. The second thing that must be there before regression can be great is called homoscedasticity. And when you're pronouncing the word, the C, pronounce it as K. Pronounce the C as K so that it sounds great. Homoscedasticity, like Russian. Now, heteroscedasticity is the opposite of homoscedasticity. Heteroscedasticity is the longest word in econometrics. 18-letter words. Heteroscedasticity. What is homoscedasticity? Forget about history. The word homo is like things being one, constant, homogeneous, homosexual, homodynamics, homotheticity, and all of those. So homo looks at something that is the same. The error, and please know that every assumption we are talking about so far is about the error. The error, you see, this one is looking at the center of the error. And we are saying that the mean talks about the center. It's the measures of central tendency. We have the mean, the median, the mode. And after you normally talk about the center, you go to the deviation from the center, or the variance. The variance must be constant. The variance within the errors must be constant. The errors must have a constant variance. So mathematically, it says that the variance of the error given the independent variables must be constant. Constant variance. So when you combine the first assumption and the second assumption together, what it's saying is that the errors are independently and identically distributed. That's the IID. The errors are independently and identically distributed. Okay, or let better, they're independently and identically normally distributed. Normal. With a 0 mean and a constant variance. The errors must be normally distributed. That's the first one. And it must have a constant variance. What do we mean when we talk about constant variance? You see, when you look at the errors, when I plot the errors, and you see this later, there mustn't be a pattern. There must not be a certain pattern where you can see that they are moving in this pattern. When you plot it against a fitted value, against a predicted, there mustn't be a pattern, because when there's a pattern, that pattern can influence the relationship. There must not be no pattern. And that is because the variance itself is the dispersion. And so you want to understand this heteroscedasticity. We'll get into it deeply. But then that's the meaning of homoscedasticity. It should be that. The moment there is a pattern, you can track a certain pattern. That is heteroscedasticity. And that means that the variance is no longer what? Constant. These two assumptions are very key, and they are all about the errors so far. Next one. No autocorrelation. No autocorrelation. Again, it is about what? If you check it carefully, the autocorrelation assumption is about what? Who can tell me? What is it about? Is it about the dependent variable or the independent variable or about the errors? Which one?
It's about the error.
It's about the errors. So watch it. The most powerful assumptions are all about what? The errors. This is the error. Now, guys, don't be scared about autocorrelation or serial correlation. I'll show you. Suppose you have X variable and Y variable, and X is 20, Y is 40, X is 10, Y is 30, X is 15, Y is 35, okay? And then you try and estimate everything, and then you got a section here called errors. Okay, this is error. Now this is for company A, company B, and company C. Company A, after estimating everything, it will have its own error. Let's say the error is -2. The error here is +4. The error here is -6. Okay, let's say I'm just making some assumptions. And these are the errors. Now, this first error for the company A is said to be error I. This second error for company B is said to be error J. And then maybe the other error is error, something K or something. It keeps going. Or because they are these letters, I could have said that this is error A, this is error B, this is error C, so that it comes according to their company names. What we are saying is that the error A and error B, they must not depend on each other. It is like this guy experienced some company problem. Maybe there was a change in CEO. And then this one too experienced a change in CEO. And this guy's change in CEO was because these people changed their CEO. That is also why they are changing their CEO. No. There must not be any dependency. They must be uncorrelated. They must be orthogonal. The word orthogonal means that they are not correlated. Whilst one is going here, the other is going here. This, when I draw perpendicular line, you see how a perpendicular line looks like. Whilst one is going here, horizontal, the other is going here, vertical. That is orthogonal. Unrelated at all. One is going horizontal pathway, another is going vertical path. So not even another horizontal, the opposite way, no. The errors must not be related to each other, must not be dependent with each other, must be orthogonal to each other. This is sometimes called covariance. So the covariance between error I and error J should be 0. The covariation should be 0. And I, that is the error of the first observation, should not be related. It's not the same as the J. So these are completely different companies, or completely different households, or completely different organizations, or completely different countries. Let's take, for example, if a household has an income, so let's say a particular household I has a consumption. Let's say these guys are living in Choco, Mani or somewhere, Choco, and their consumption is maybe 20 cedis a day. Let's say that a household consumption is in East Legon, and they are consuming 1,000 cedis a day. And this household's 1,000 cedis they are consuming, it is greater than the expected. They are consuming what they are expected to consume. So maybe they are expected to consume 800, but they are consuming 1,000. Given their income, okay, given the income level. Because of that, you think that since the guy in East Legon is living in a posh area, and another guy in Cantonment is also living in a posh area, then we are expecting the guy in Cantonment consumption to be high compared to their income, because they are all living in what? Posh areas. Then the way this guy's own is behaving, this guy's own should also behave equally, implying that the two of them have some positive relationship. Whether it's positive or negative is irrelevant. But no, you cannot make that assumption. There is no reason to assume that. If you do that assumption, then there's autocorrelation, and you should not have autocorrelation in the errors. Guys, do you understand? This is the first time I've explained it well. But normally I jump. And this is how. So there must be no autocorrelation. There must be no heteroscedasticity. And then the error term must be 0. The mean of the error term must be 0. These are the 3 assumptions you've looked at so far. Let's move on. The next one is, so remember what I just said some few minutes ago was not about independent variables. It was about errors. And in fact, the last one I even looked at was about 2 different errors. Now let's look at between the error and rather the independent variable. Between the error and the independent variable. Again, the 2 of them must not be correlated. So the consumption of a particular thing. So any particular error must not be related to the independent variable. Okay. And this relationship is dangerous. So we call it endogeneity problem. And it's a very big you can write a lot of articles and handle endogeneity in different ways. So when you have the errors depending on the independent variable depending on the errors or vice versa, then you have the problem of covariance. But there must not be any covariance, or there must not be any dependency between the errors and then the explanatory variables. This is known as the covariance of the error term, and that of the independent variable must be 0. No endogeneity should be present. So that means that we are talking about, we've already spoken about an error and then an error. And now we're speaking about an error and then an independent variable. Now we can talk about an independent variable and another independent variable. Take note of all this. And that is known as something else. We'll come to that. We'll come to that. It's called multicollinearity. We'll come to that. But let's look at one more assumption, linearity in parameters. Linearity. What does that mean? Very simple. That one is very simple. The relationship between the x and the y, that is between the dependent variable and the dependent variable, must be linear. The relationship must be linear. So model the relationship as a linear relationship, unless there's a strong reason that there is no linear relationship between the variables. The relationship can be linear in regressors, but they must never be linear in parameters. Now, in order to handle this linearity, which we shall look at later, okay, if there is a problem, let's say that your regression is supposed to be linear. It must be linear in parameters. But you realize that your results are not good. It means that it might be that they should have been nonlinear, but you made it linear. In this case, you may have to introduce logs, logarithm, natural logs. You may have to square some variables. Okay? You may have to interact some variables. These are things you would do. You do it even in your practical work, I'll give you. Okay? You have to decide which one do I have to take the natural log? Which one do I have to take the squares? And what is the essence of doing that anyway? Which ones do I have to interact with which one? What is the theoretical justification for that? You have to do that to be able to handle any possible problem. But the general thing is that there must be, for example, if you look at the relationship between price and quantity demand, there is a linear relationship. There is no non-linear relationship. There is no quadratic. What that means is that we always know that a rise in the price of a good will lead to the quantity demanded, a fall in the quantity demanded. So whilst one is, so the line is linear. As you draw a line like this, okay, as you draw a line like this, it means that if the price is this and the quantity is that, as the price falls here, the quantity will rise there. Okay. So as the price is falling, quantity is rising. So there's a linear link. But it's not like as the price falls, quantity rise. But when the price falls again, then quantity quantity falls. Okay. When you have a mismatch, and it can happen in practical life, such a nonlinear thing can happen. For example, let's take the relationship between size. So if you have size of a company, and then you have maybe the profit of the company. As the size of the company increases, let's say the number of people are increasing, profit will rise. As the number of people are increasing, profits will rise further. So as the number increases, profit rises. As the number increases further, profit rises further. But it gets to a point, as the people are getting too big, they start shaking. They start lazing about. You don't even monitor them well, because they are too big. Now, profit rises, to get to a point, profits start falling because you're paying a lot of money for these people. So profit rises, but it gets to a point, it starts falling. So there's a diminishing marginal returns to increasing your size. So in this case, size doesn't just take a linear relationship, but you must have size also taking a non-linear link, a quadratic link, to indicate that size can rise and fall. So in the model, you will have size, okay, as one of the independent variables, but you also have size square as another independent variable. In this case, there's a justification for that. You see, when I was talking, I used like some of them will be checking, some of them will be lazing about, there will be difficulty in monitoring. The CEO doesn't know everybody, and it's difficult. And that's what you see, by the way, in the ministries. That's what you see in the government sectors. It's so large. It's so large. You can't even know who is doing what. Somebody watching cantata, somebody watching movie, somebody will be fooling about, somebody will be reading newspaper from morning till evening. Some will be talking about politics because there's no monitoring. There's no camera monitoring. There's no supervision. There's no nothing, delegation, nothing. Guys, are you with me? And that should be modeled into the work. So that is on rare occasions where you can have nonlinear relationship, where size doesn't help, but generally size may help. So when there's that theoretical justification for it, based on the literature, you can now make that. Other than that, the relationship is linear. Cool. Now, the one I said before about the independent variables. Remember I said that there's also a situation where you can have two independent variables and you don't want them to be related to each other. So we looked at a situation where we have autocorrelation. There's supposed to be no autocorrelation between the errors like this. And then we said that there's also not supposed to be endogeneity. That is no covariance between the errors and then the independent variable. Now, we are looking at two independent variables. And this is where I would define multicollinearity for you guys. It's not in the document here, so you should write it down. First of all, what is multicollinearity? By the way, first of all, you should know that multicollinearity is basically about the independent variables. Multicollinearity is about the independent variables. Oh, sorry. Okay, let me move on. So, independent variable, let me define multicollinearity here. Multicollinearity exists when two independent variables, xi and sj, are so correlated that it becomes difficult to disentangle the partial effect of one from the other on the dependent variable. Multicollinearity exists when two independent variables are so highly correlated. They are so highly correlated that it becomes difficult to separate the partial link or the partial effect of one of these variables from the other before you look at its effect on the dependent variable. So let's take a variable like experience and education. Suppose that in your company, they say that in your company, it is said that anytime you get 5 years of experience in the company will give you full scholarship to go and do your PhD. This is a rule in the company. So when you join the company, you are 3 years, but you didn't know this. So you saw that a lot of people are being sent to go and do their PhD. Oh, and by the way, when you come back after your PhD, your salary will be doubled. And after being in the company for 3 years, you saw people going for PhD. 3 years, some of them have finished, they've come back, and their salaries have been doubled. You are quite unhappy. Your boss sees that, and he asks you, what's the problem? You said, well, I don't know what's happening. Your boss said, oh, you didn't know the rule. The rule says that you must be 5 years old in the company. After that, you'll be given a full scholarship to do your PhD. After that, you come back and your salary is doubled. Okay, good. Now you get it. You know you have how many more years to go? 2. 2 years come, and now you have 5 years. Truly, you are sent with a full scholarship to go and do your PhD. You return to the company after 3 years of doing your PhD, and guess what? Your salary was truly doubled. Question: what led to the increase in your salary? Was it the 5 years of experience or the 3 years PhD that you did? Who can tell me? Was it the 5 years of experience or the 3 years PhD? Which one led to the increase in your salary? Samsung.
I think it is a 5 years of experience because
5 years. Don't worry, I get it. I get. Don't worry. Don't give a reason. I just want to know which one. Francis, which one?
Well, I am thinking both must be true for your salary to be increased.
Both. Okay, Benjamin. Benjamin, what do you say? So you have now part of the reason why.
Sorry, I also think. Sorry, sir. I also think it's the both.
All right. The reason is, by the way, is neither. And if it is both, it's because the two are multicollinear. You see, the reason why you may struggle to know which one it is because the two variables are multicollinear. Multicollinear because they are too close to each other. Because it is your experience that is influencing you going to the school in the first place. So your experience is influencing you going to the school to do your PhD. And you going to the school is also dependent on you having the 5 years of experience. So experience is influencing education, education is influencing, and both of them are now influencing your salary. We don't want that to happen. We don't want a high multicollinearity between two independent variables. You call yourself independent. Your experience is independently affecting salary. Education is independently affecting salary. And yet, both of you are correlated with yourselves. And once both of you are correlated with yourself, that leads to what is known as what? Multicollinearity. You don't want that to happen. And we'll handle this as we go further. So one of the assumptions of the regression is that there must be no high multicollinearity. We need exogeneity of the independent variables. The independent variable must be exogenous. That is not influenced, not themselves affected by anything. Not affected by the error, not affected by any of the independent variables, and not affected by an unknown variable that is not even in the model. They should only have a relationship with the dependent variable, the outcome, the response. But if it is there, if multicollinearity is there, first you have to detect it and cure it. You detect it by using variance inflation factor, and you cure it by removal from the model and readjusting the model. Sometimes you don't even do that. You go straight to do ridge regression that we spoke about. When there's too many multicollinear variables, ridge regression will solve the situation. So you got to run ridge regression and look at the situation. Cool. That is another assumption. The next one is that there must be no specification bias. Okay, if a variable should be square and you don't give it a square, if it should be cube and you don't give it a cube, you have a specification bias. So try and correctly specify the model. If you don't specify the model, the OLS parameter estimate will be biased. Oh, it will no longer be blue. It will no longer be blue. Blue means best linear unbiased estimator. There must be best, minimum variance, must be linear, must be unbiased. Okay. And then, of course, the expected value of the beta cap should be equal to beta. But this might be affected. That is unbiasedness. What is the beta cap? Remember, the beta is the parameter estimator. We don't know it. It's unknown. It's unknown. That's why we collect data. We sample data. Remember, this is a population parameter, beta. But we don't know it. It's unknown. So we take a sample and then we estimate it. We mimic the real world. But the real world is unknown. And so whatever you get is beta is capped. It's capped means we've estimated from using a sample. If that sample is not representative of the population, and when we say population, we're not talking about population of your companies, because your company is interacting with people in the world, others in the world. So they are all part of the world. And that world is the true beta, this one. And this true beta is unknown. And so you estimate it. Our goal is to make sure that the beta cap is closer to beta. What we have estimated is closer to what is in the true world. And if it is closer, then we say that it is unbiased. If it is not closer, it's biased. How do you know whether it's closer or it's not closer? Don't worry, we'll see. But that is all of these assumptions of the OLS. So, well, these are the major assumptions of the OLS that you want to know about. Okay. Know these assumptions. because you got to use this assumption to run your matrices. Everything we have done to estimate the beta naught and the beta cap that we have done today, please remember that we can use matrices to do that. We can use matrices to do that. Why should we use matrices to do that? We'll look at that next time, but I want you to know that matrices is what the software is using. That's what Excel is using. That's what R is using. That's what Python is using. That's what MATLAB is using. That's what Stata is using. Shall use matrices. So you got to understand a bit of how matrix develop that. I saw a question. Who was asking the question?
Yeah, Doc, Noah here. So must all these assumptions be met to be able to run your regression?
Well, first of all, you will run a regression. Then after that, you will check if they have been met. If they have not been met, you ensure that you meet most of them. And yes, you should meet all of them. If you don't meet all of them, you should explain why that is so. Sometimes you cannot meet everything, but you should explain why that is so. That's the key point. Explaining why it is so is more important than not checking at all. Sometimes there's nothing you can do. So yes, of course, things. But you have to explain why that's so.
Okay, thank you, sir.
Benjamin.
Yes, sir. Please, can we have a situation where you will not meet half of them?
Yeah, then you don't have a good model. But then that's saying you will not meet half of them. You will have to now do something about them to meet half of them. And that one, there's a way around it.
How do we do it, please?
Oh, that is the essence of this whole course. We shall do that step by step in our data set.
Oh, okay.
Yeah. So that is how you go. I just wanted you to know this assumption because we will use this assumption. Yes, Obed.
Okay, yeah, Doc. Please, does all the assumptions that we've mentioned, does it apply to all the data types, the 3 data types?
Yes, and in fact, the other ones have other assumptions. This one is the basic one. The other ones have more that you got to meet. Because those data types are more complex than this. This one is cross-sectional data we are looking at. Time series, they will require you to have assumptions of stationarity and other things. Okay. Panel, you have to have more assumptions to deal with, cross-sectional dependency, time series dependency, panel dependency, several things. These are basic assumptions. But the ones that are, the other assumptions that you have to consider are not more than this. Maybe 2 or 3 more. They are not more than what we looked at because they all have this. Now, with this assumption in mind, guys, what you want to do is to go through the slide on how matrices can be used to derive the betas. This one, this beta cap, how you can use matrix. I want you to have this in mind that in a multiple regression, this x's, x1, x2, x3, they become plenty. And so we use capital X to represent them. And the beta 1, beta 2, beta 3, beta 4, they also become plenty. And so in a multiple regression, we use 1 beta to represent them. In a multiple regression, we use epsilon, okay, without the I, to represent all the errors. So I just want you to know that this is the general way of formulating the multiple. And we have to learn how to go through these step by step and to be able to find the beta, and go through this step by step and to be able to find the variance covariance metrics. This is very important. Why we need to go through all of this. Then after that, we'll come into the real work of how to achieve this basic regression in a practical form in R. So that's what we shall be doing next time we meet. But please go through these things. I've written it. What I do is that I try to write my things with a lot of explanations, enough for you to be able to follow through. When you have not looked at it before you come, then obviously you find it a little bit wanting. But now that you have it, when you look at it before you come, as I go through, you say, oh yeah, oh yeah, oh yeah, oh yeah, oh yeah. Now you have the slides, look at it before we come. And write the R codes before we meet. All right. Any other questions?